Okay, so thank you all for coming. It's my great pleasure to introduce our speaker. It's a special speaker and a special seminar because it's Professor Weimin Zhou, who just joined University of Arizona. He holds a joint appointment in the College of Optical Sciences and the Department of Medical Imaging in the College of Medicine. Professor Weimin did his PhD in electrical engineering at Washington University, then did a postdoc at UCSB. And then later he became an assistant professor in Shanghai Jiangtong University. Okay, and then he fortunately for us, joined us. And his work is mainly on AI in medical imaging. And so we're very fortunate to have him here. And this is our sign of appreciation, a button that I didn't get last year. Thank you so much. Thank you all very much.
Thank you so much. Thank you so much for your introduction. Okay, great. Thanks so much for your introduction and also the certificate and pin, and I'll keep that. And good afternoon, everyone. And thank you all for joining me today. And is that okay? Can you hear me? Okay. Yeah, great. And it's a great pleasure to have this opportunity to share some of my work on the ideal observer, which is very important to image science and vision science. Actually, the image science group in optical sciences has a long-standing tradition of leading advancements in imaging research. And actually, since I was a PhD student, I have admired work of image science pioneers here in optical sciences, such as Dr. Harrison Barrett, Dr. Carl Mayers, and Dr. Matthew Kupinski. And so this is why I feel deeply honored not only to give this OSC colloquium, but also to be part of the OSC to advance the future of image science. And also, actually, today is also a special day for me because today marks the exactly 1 month since I officially joined the University of Arizona. So this makes this moment even more meaningful to me. Okay, so let's get started. So I'm not going to talk about specific modalities in imaging today, but instead of that, I'm going to talk about some general concepts about how to assess image quality and how how do we do research by use of ideal observers for both the image quality assessment and also medical image perception, and also talk about some challenges when we implement ideal observers, and also the machine learning ways for possibly address some of those challenges for various tasks by use of different techniques such as supervised learning, generative adversarial networks, and reinforcement learning. Okay. So I just want to first give this very general description of medical imaging systems. So an imaging system is a device or mapping that maps from object property to image data. So we can think of that as a typical engineering black box. We have the object input to the imaging device, okay, which is F, and then we have some image device that maps from this object property to a data, okay. So as an example, in X-ray computed tomography, the object property to be imaged will be the linear attenuation coefficient, and the measured data would be sinogram, which is a collection of line integrals of the object property. Okay, so this process from object to measured data is also known as a forward problem, and it can be mathematically described by use of this equation G equals HF plus N. Right, so here the G is measured data, H again is image operator, F is the object to be imaged, and N is the measurement noise. Okay, so in general, the measured data will not be the final image, right? And then typically we will need an algorithm or software to further process the data to form the final image, and from the data to the estimated image of the object will be referred to as inverse problem. All right, so then it is important to keep in mind that such imaging systems, having both the hardware component and the software component, will have many tunable parameters to be specified. And it will be, when you will design new imaging system, or if you want to optimize an existing imaging system, it will be important to choose those imaging parameters in a smart way. Okay. And here is an example to show the impact of imaging parameters on the produced images, right? So in this case, I show two images of X-ray CT through the same, through the chest of the patient on the same section of anatomy, and the two slices were produced using different data acquisition and the reconstruction parameters, and we can see that the left one corresponds to the thick slice thickness, and the right one corresponds to the thin slice thickness, and clearly we see that the image on the right has sharper appearance and seems to have higher resolution. All right. So then does that mean the right image is better than the left image? All right. So then we need to choose the right image instead of the left image. Actually, to answer such question, it will be important to identify the purpose of the imaging task, right? So for example, if our purpose is to just to identify some abnormality for corresponding to pneumothorax, things like this, then I would say, okay, the image on the left will be sufficiently good for identifying such structure. Then I probably would choose the left image because the left one corresponds to a lower radiation dose. Okay. So then to talk about the image quality and which one is good or which one is bad, it will be important to actually have to quantify the information containing in these images to answer such question for us to make a comparison. So then, following up on that example, I want to talk a little bit more on image quality. So then when we want to evaluate or explore, design our new imaging systems or even optimizing an existing imaging system, we want to have a figure of merit that summarizes the image quality, right? Then, potentially when we talk about image quality, the traditional image quality metrics might be something that we normally think about, such as a resolution or image contrast, noise level, and mean squared error in computer simulation studies. Actually, all of these measures are based on the physical or statistical properties of an image. So they are commonly used in image processing literatures, but actually, commonly they are not very good at assess medical image quality. And to see that, I have just included this toy problem example to show the limitation of traditional or physical-based image quality measures. And this figure is actually from Dr. Kupinski. So then in this example, we have 6 images, and on the top row, far left image corresponds to the original image in which we have a small signal or tumor embedded in a so-called lumpy background, which represents some textures in medical images. And then the other 5 images correspond to some perturbed images that are formed by use of processing operators or adding some certain level of noise. And we can see that these all 5 images look very differently, right? And the different appearances of those images will also lead to the difference in the signal visibility, right? So for example, in figure C, we can barely see the signal, right? So if you compare it to the other 4 images, right? So then, but they all have the same mean squared error. They all have the same MSE, mean squared error. So then, if we use the MSE as a figure of merit to assess or to compare these images, we will treat them equally, all right? So which is very misleading. So then that brings us to the task-based measures of image quality. So then, because what we want is to actually measure the image quality based on how well an observer can achieve for a specific goal or specific task in clinical settings. Okay. Then to achieve this, we want to maximize the amount of task-relevant information so that doctors or radiologists can be able, will be able to see tumors or other abnormalities in images. Okay, so in the field of medical imaging, this is what we really want and advocate. So more formally, task-based measures of image quality quantify, the performance of an observer for a specific task. And of course, that task can be, classification task or estimation task. Okay, and such task-based measures of image quality will be affected by many factors, including statistical properties of objects, because we want our imaging system to be used for an ensemble of objects or patients, right? So there will be randomness in the objects to be imaged. And then, of course, imaging systems. That is why it is important to choose the right imaging parameters to design your imaging system, right? And the task of interest, what task you want to focus on, is that the signal detection task or localization task or estimation task. And then, of course, we want to compute the observer's performance that summarizes your image quality. All right, so actually, this is just a very brief review of task-based image quality. And this book, Foundations of Image Science, from Dr. Harrison Barrett and Dr. Kyle Mayers, actually, comprehensively summarize the model observers and rigorously defined the task-based image quality measured. And this book has made a tremendous impact on academic, industry, and the FDA. And actually, Dr. Harrison Barrett has been a pioneer in this field of image science, and he's now retired from optical sciences. And his student, Dr. Karen Mayers, who graduated from optical sciences, also went and lead to FDA group and set up a set of regulatory rules and image science framework that enable companies to do scientific studies for their medical imaging systems to maximize diagnostic performance. Okay, so then talk about diagnostic performance. Of course, we want to maximize that, but then besides the image quality that can contribute to the diagnostic performance or errors when we interpret images, the inherent limitations or physiological constraints of our human visual system will also contribute to the errors, right? So then it is important to also understand the human visual perceptual processes or decision-making processes, such that we can further advance the image processing or enhancement or display techniques for achieving a better diagnostic accuracy. And here, in this example, I just show you an example of the search arrow in which the target to be detected, and there's a tumor actually is actually indicated by this large circle on the right lung, on the right image, right side of the image, and then these right lines indicate the eye tracking record of an observer, right? So we can see that the observer missed this target, and then the observer never fixated at the target, and then did not report that target. Okay. So then the Bayesian observer. So why is it so important in the field of image science and also vision science? Because the Bayesian ideal observer is a theoretical model that sets an upper bound on observer performance, right? So then it will be very powerful to actually summarize the total amount of task relevant information in your images, such that you can use that as your figure of merit to guide your optimization of medical imaging systems. Okay, so then and also because the Bayesian observer is has the best task performance, so then it has been also usually used as a benchmark model to explain or understand or evaluate the efficiency of human observers or other suboptimal observers. It is also a commonly used tool as a starting point for modeling human perceptual processes by incorporating the physiological constraints of human visual systems. Okay, so before I dive deeper into the Bayesian observer, I want to give this a very brief crash course on the observer performance and ROC analysis, right? So just to set up and that you'll be ready for the ideal observer computation. So here I just show this very simplified example of binary classification. Suppose that we have a group of people that we want to classify this group of people as satisfying two classes. One is the people without disease or hypothesis H sub 0. The other group is people with disease, the hypothesis H1. all right? So we want our observer to make a decision, okay, for each case. So then we have some notations here. Let D sub I denotes the decision made by our observer, saying that the hypothesis H sub I is true, okay? Of course, that decision can be correct or incorrect. How does the observer make such decision? The observer, to achieve that, the observer computes a scattered test statistic from the data, okay? Through some functions. Of course, that function, different functions will correspond to different observers, all right? So the Bayesian ideal observer by definition employs the best possible function to compute such test statistic. Then we can make a decision by simply compare this scatter test statistic against to a predetermined threshold or cutoff T sub C. All right. Of course, this T sub C can be changed as well. All right. So then, based on the two hypotheses and the two decisions that the observer can possibly make, we will have this table of 4 decision states. All right. So this which correspond to 2 correct states and 2 incorrect states. All right. So then having observer compute the test statistics for each group of the hypotheses, then we can for each of the group we can draw this distribution of the test statistic. All right. And for this binary classification task, then we have these non-diseased cases and diseased cases and correspond to 2 distributions, right? And then we set up a threshold or cutoff T sub C to make a decision. Then we can have some ideas about how so what will be the correct case and incorrect case, right? So for example, if we have some non-diseased cases that will be having test statistics less than the threshold, then we can correctly identify that case as a normal or a negative case, right? So which is corresponding to the specificity or true negative fraction. All right. So similarly, if we have cases that will be having the test statistic that is larger than the cutoff T sub C, then those will be corresponding to the false positive fraction. All right. So similarly, we'll have the false negative fraction and the sensitivity, the true positive fraction. All right. So then, of course, we again have 4 values here, but we can see that we can only we just need to use only 2 values to comprehensively describe this performance, right? Because, for example, the FPF is 1 minus TNF, and similarly we can have these just 2 of those quantities to describe this performance. For example, let's use the TPF and FPF then. Okay, if we use a pair of quantities TPF and FPF, and then we can draw this point in this plot. Okay, and which in which the horizontal axis corresponds to the FPF, which is 1 minus specificity, and the vertical axis corresponds to the sensitivity, which is the TPF. Okay, we have this point at that threshold. All right. Of course, we can change our threshold to another threshold. Then subsequently, we'll have another point. Okay. So when we actually vary over the entire range of the test statistics, then we can plot this complete ROC curve, right? So that will be a summary of the observer's performance for such a classification task. And then we can also use the area under the ROC curve as our final figure of merit, to assess observer's performance for image quality assessment. All right. So then, having introduced the observer's performance, then we also want to find out which observer is best, which can maximize the observer performance, which is I have just give a brief introduction to the Bayesian observer, but here is more details. The Bayesian ideal observer is the one that minimizes the Bayes risk. All right. So for this classification example, the Bayes risk is defined as the average cost when we are making decisions. Okay. For example, first of all, we can predetermine some of the cost values, C11, C01, etc. For example, this C11 corresponds to the cost if our decision is D1, but actually the case is the ground truth is H1 hypothesis, right? So similarly, we can define the other cost values. So it can be shown that the Bayesian ideal observer employs this decision strategy that minimizes the Bayesian risk, in which we have the likelihood ratio, and then we compare this likelihood ratio to a threshold T sub C, and this T sub C is corresponding to both the prior probabilities of two hypotheses and as well as the cost values that we have defined. All right. So here is a special here is a special case. Here is an example. If we define our C10, C01, which means that the cost for the incorrect decision to be 1, and then for the C values corresponding to the correct decision will be 0, then this C bar becomes the probability of error. Then your ideal observer will become the minimum error detector, right? So if we take a closer look at this decision strategy, then that is also corresponding to the maximum or posteriori probability or MAP criterion. So it can also be shown that the Bayesian ideal observer is associated with the Neiman-Pearson criterion that maximizes the true passive fraction given an upper limit of the false passive fraction, right? Which means that the Bayesian ideal observer will optimize every each point on our OSC curve that can lead to the maximum AOC value. Okay, so then but of course you probably will already be aware of that this likelihood ratio typically is unknown. Okay, so except for very simple cases in computer simulation studies, for example, if you generate the Gaussian field as your images, then you can analytically determine this likelihood ratio. But in most cases, when we are dealing with more complex medical images, this likelihood ratio is unknown. Right? It doesn't have an analytical formula for that. So then somehow to yeah.
So in the previous slide, for the Neiman-Pearson maximizer be fulfilled, shouldn't the parameters of the data be known a priori? But in principle, you have mentioned that the tumor, for example, characteristics could be taken from an ensemble. So we don't know exactly the parameters of the data.
Yeah.
So shouldn't be as far as I know, the Neiman-Pearson maximizer only is fulfilled when you have the full knowledge about the parameters of the signal.
Exactly. Yeah. So the Bayesian observer requires the full knowledge about everything, actually, the image data, the signal, including signal and background noise statistics. So this is a theoretical model that assumes they know all of the required statistics to compute this model. Exactly. Yeah. Yeah. Okay. That's a very nice question, by the way. Then because we don't, in most cases, we don't know how to compute the ideal observer, the Bayesian observer, then researchers have, imposed some constraints on the computation of the ideal observer. For example, let's just impose the linear function constraint. Okay, let's just constrain ourselves by use of linear function. Then there is an ideal linear observer, which is known as a Hotanian observer. All right. So in that Hotanian observer, we just compute our test statistic through this inner product between the data and the template. Okay. And the Hotanian observer, by definition, maximizes the signal to noise ratio of the test statistic, which is also another commonly used metric for evaluating signal detection performance. So then the Hotanian observer's template W sub HO can be computed according to this equation, in which K sub 0 and K sub 1 correspond to the covariance matrix of the data under the two hypotheses, and the delta G corresponds to the difference of means in the data under the two hypotheses. All right. So although this is great that we have the analytical formula for computing the Hotanian observer, but it can also be very challenging because if you want to directly compute such Hotanian template, we have to estimate and invert covariance matrix, which can be enormous for large dimensional image data. All right. Okay, so we have some challenges in computing ideal observer and Hotelier observer. So how do we solve that? How do we find another way around? Okay, so then we look at the machine learning community. Okay, so there are some general rules or general tips for using machine learning about when to use machine learning. All right, so when the problem has no analytical solution. Okay, that's exactly the case when we want to compute the Bayesian ideal observer, and then. Or it's very difficult or to directly program or compute a model. For example, in our case, that can be our Hotelier observer case. And of course, to be able to establish a machine learning model, we have to use data. Okay, a huge amount of data. So then, but luckily, so when we are evaluating imaging systems, it will be commonly performed in so-called virtual imaging trials or virtual imaging studies, in which we use computer simulation tools to generate data and then tune the parameters and see how it will perform for our task of interest, right? So then if we have such computational tools in virtual imaging trials, then we can generate large ensembles of data from a so-called stochastic object model, right? Which is a model that can produce objects following some prescribed statistical properties. So of course, the stochastic object model can be mathematical models, for example, lumpy object model, type 1, type 2 cluster, and I think the pioneers here in optical sciences are already also involved in this creation of lumpy object model. And also the stochastic object model can also be learned by use of machine learning or deep learning method, right? So for example, we can, what if we use a generative adversarial network or other techniques, for example, diffusion models, or other generative models to learn to establish a stochastic object model. Yeah. So that really depends on your image modality, right? So if you have MRI, I would say, for example, you have 256 by 256 size of the MRI images, but you have a CT that could be over 1000 by 1000. So that could be huge Coherence matrix because, for example, if you have m by m image size, then your Coherence matrix will have the size of m squared by m squared, which is enormous, right? Okay. So then. Okay, here we go. So then, okay, let's assume that we are in the virtual imaging trial, and in which we have stochastic object model that can generate large ensembles of data. So then, having such data, what should we do to approximate Hotelier observer or ideal observer? Okay, I will start with the Hotelier observer. So again, just a reminder that the Hotelier observer, by definition, is the one that maximizes this SNR of test statistic. Okay, so then we can actually, to achieve that, we can design and solve this constraint optimization problem in which we want to minimize the average of variances of the test statistic, and at the same time we want to fix this difference of means of the test statistic. Okay, and to solve this constraint optimization problem, we can come up with a Lagrangian function, right? So then we can write up the Lagrangian function with multiplier lambda, and then we can show that the minimizer of such a Lagrangian function would be the W star equals lambda and K0 plus K1 inverse, and S is a signal or delta G. All right. So then if we set lambda equals 2, then we have exact form of W sub HO. Then based on that Lagrangian function, we derive the new loss function for yeah, go ahead.
In the previous slide, so I think W here is the observation weights for each pixel. I think in the image, as far as I understand.
Exactly. Yeah,
I see. So shouldn't be there also another constraint on W as some sort of observation time or something that is allocated?
No, actually, no, because solving this constraint optimization problem is equivalently to maximize this SNR sub t, so there's no other constraint that we need to put. But but somehow I'm not sure if you want to, for example, normalize the W or things like that. But you can do that afterwards. But for now, you can have this W, and it will be shown that this is a convex problem. Right? Yeah, exactly. Yeah. So then, so then we can find the global optimal, right? So here is not a local optimal, it's a global optimal because it's a convex problem. And then based on this, we can, based on this Lagrangian function, we can just derive our loss function for use in the supervised learning to directly train the W. So you can see that from during the training, right? So we just threw in the data and the corresponding labels. We don't need to, explicitly estimate or invert the Crohn's matrix, right? So we just have this, vector W to be learned during the training, right? We directly work on W, no longer the Crohn's matrix. But of course, following this framework, we also find that, okay, we can also employ the covariance matrix decomposition, right? So which actually decomposes your randomness of the data into two components. One component is associated with the background, another one is associated with the noise, right? So in your computer simulation study or virtual imaging trials, you can generate the background only, and then the noise statistic, right? So we can just efficiently incorporate those knowledge into our new loss function, which can be used for more efficiently train our Hotanian observer. Okay, and then so then after training our Hotanian observer, somehow we still want to see the best performance of an observer for a specific task, and we still want to approximate the Bayesian ideal observer, which might be a nonlinear function of the data. So of course we don't know the formula of the likelihood ratio, but then what we want is to have some function approximator to feed the data, okay, such that we can have approximated version of that nonlinear function that can be used for approximating ideal observer performance. So then what would be a nice function approximators? Neural networks, right? So neural networks are known to be a universal function approximator. Here I just show very simple toy problem example. Right, so here are two neurons, and each neuron represents a computational unit that takes some signal in and then output a signal for use in the next step. Then in this case, if we carefully design our weight parameters of these neurons, we can come up with this rectangular function with this t sub 1, t sub 2 parameters. Then if we add more and more neurons, okay, of this unit, we can have a function that is a combination of these rectangular functions, which we can see that it will approximate a very complex nonlinear function. Right? So that's a very simplified idea behind the neural networks as a universal function approximator. So of course there are many neural network architectures. So possibly the most commonly used neural networks will be the fully connected layers neural networks, right? So in fully connected neural networks, in which they use fully connected layers, which means that each neuron in a hidden layer will be fully connected to all the previous neurons. But for imaging research, it will not be very efficient because it will introduce a huge amount of weight parameters need to be specified during your training, right? So but in image study, because image has certain properties like the spatial temporal correlation that can be efficiently used by use of convolutional operators, right? So then they came up with the convolutional neural networks that employ the convolutional operator in the neural network, right? So then we use the CNN, the convolutional neural networks, to try to approximate an ideal observer, right? So again, the ideal observer, if we want to approximate ideal observer, it will be ideally to approximate the likelihood ratio. But we are not going to directly to do that, all right? Because it will be easier if we transform this likelihood ratio to a posterior probability, which is a monotonic transformation of the likelihood ratio, so that will not affect your ideal observer's performance. Then to do that, to approximate that posterior probability, of course, we set up a CNN that is, parameterized by a set of weight parameters theta. Then we also design our CNN to output, a probability by use of a sigmoid function in output layer. All right. So then the goal is to approximate this ground truth probability by use of the CNN model probability. But how do we do that? We don't know the ground truth probability, right? But what we do have is the label data. All right, we do have, for each of the training sample, we have the labels that associated with its ground truth. So then we can minimize the cross entropy loss function between the predicted or model or CNN modeled probability with the one-hot vector associated with the labels. It can also be shown that minimizing this cross entropy loss function is equivalent to have the maximum likelihood estimate of the parameter theta, right? So then for the signal detection localization task, okay, so if we consider a signal detection localization task as the one that in which the signal has j possible signal locations, then it will also become a classification, multi-class classification task. All right, so here is a setup of such signal detection localization task in which signal absent H0 and also signal present at location j. Okay, and to perform such task, scanning observers were proposed in which we compute test statistics at each location of possible signal location, and then the predicted signal location will be the argmax of that test statistics. And then we decide if the signal is present at that location by comparing the maximum of those test statistics to a threshold tau. Right? So if that is greater than tau, then okay, the signal is present and at the signal location j. Otherwise, we decide the signal is absent. All right. And then for such tasks, also there were studies that that propose the Bayesian ideal observer that maximizes the corresponding performance, which is measured by a so-called localization ROC curve. All right. So in Kurt and Gindi in their TMI paper in 2005. So then we found that the decision rule, which is the modified generalized likelihood ratio task that maximizes LROC curve, will be equivalent to a posterior ratio task. All right, according to the Bayesian rule. So then if we transform this, MJ LRT to the PRT, then everything will be the same as before, right? So we have this, we can approximate these posterior probabilities by use of our CNN. And then once we have done that, we can use those approximated or CNN modeled posterior probabilities in our posterior ratio test. All right, so here again, this slide is very similar to the previous slide, in which we so one difference is that instead of using the sigmoid function for binary classification task, we are using the softmax function, right? So make sure that the output of the CNN will be a set of probabilities, right? And here here shows some numerical studies, right? So in this case, in this example, we consider a lumpy background model, right? Because we want to validate if our CNN can be can be used for approximating ideal observer. And thanks to Dr. Kupinski from the previous work of the Markov-chain Monte Carlo, we can use MCMC algorithm to get a reference performance for such lumpy images, right? So then we just want to use that, take that, and then train a CNN and also our Hotanian observers to see if that can be in a close match to the reference methods, right? So that's that. And then for the signal detection localization task, this example I think is interesting because we modeled two imaging systems with actually both imaging systems are corresponding to the parallel whole kilometer imaging system with different parameters, right? So the system 1 has lower sensitivity parameter but greater resolution parameter, and but system 2 has higher sensitivity parameter and lower resolution parameter. And then we consider 9 possible signal locations, and these two images just illustrate that signal at different location. All right. So then if we consider about the signal detection localization task by use of ROC curve as a figure of merit for assessing the image system, then we observe that, okay, system 1 is better than system 2. right? So because that's reasonable because the system 1 has better resolution, right? But if we just consider about the binary classification task, just to tell if the signal is absent or not, and if we just doesn't care about the location, then system 2 is better than system 1, as indicated by the ROC curve, right? Which is also very reasonable because the system 2 has higher sensitivity. Okay. So then, of course, supervised learning-based methods have, we have investigated such methods for those classification tasks, but it has its own limitations. For more complex tasks. For example, if we now want to focus on a task that requires us to estimate the tumor parameter, for example, the size of the tumor, then it will be difficult for the supervised learning-based method to be deployed, right? Because, for example, there are some proposed figure of merit as an ideal observer performance for the estimation task. For example, from Dr. Kupinski, he proposed to use the Cramer rule lower bound on the variance on bias estimator as an ideal observer's figure of merit for such estimation tasks. And also Dr. Clarkson, who is also retired from optical sciences, and he proposed the estimation ROC curve or EROC curve and the way to optimize that EROC curve. But in either case, we have some quantities needs to be computed or test the statistics to be computed. But the supervised learning-based methods up to now there are no way to approximate to those quantities. But those quantities can be readily calculated by use of a posterior sampling along with Monte Carlo integration because they are all associated with the integral of some quantity multiplied with the posterior probability. All right. So then I want to briefly talk about this seminal work from Dr. Kupinski on the Markov-chain Monte Carlo for approximating the ideal observer. Right. So then in this case, this is a binary signal detection case in which we can rewrite this likelihood ratio by use of this integral. Right. So here we have two quantities here in this integral. The lambda sub bke, which is the likelihood ratio given that a known background, okay? So if the background is known, then the only randomness in that likelihood ratio would be the noise randomness. And because we are considering a computer simulation study or virtual imaging study, then we know what noise it is, right? So we know the noise statistics. And then we can analytically determine this lambda sub bke. All right? So the difficult thing is this, the posterior probability. So then it is very difficult or intractable to directly compute this integral, but luckily we can use a sampling-based method along with the Monte Carlo integration to numerically estimate this integral. Right, so this is so-called we can use a Markov-chain Monte Carlo method to sample the background B or its associated SOM parameter theta from this posterior probability, and then we do the average on that. That will be the estimate of this integral. Okay. And of course, Dr. Kupinski's MCMC method has been demonstrated to be, ready or straightforwardly adapted to approximate I/O for complex estimation tasks. And in their papers, they have already demonstrated that, right? So the thing is that such MCMC method, if we want to implement that, we have to, sample data from the SOMs. Which is very specifically designed for each SOM, right? So then, previously there are some applications or implementations of such MCMC method for relatively simple object models, such as lumpy object models. But it will be also important to extend such this method's ability to use for more complex scenarios, right? So then we come up with the idea to use generative models in deep learning, right? So because once we have a generative model trained from deep learning, what we have is a generative model that can take a latent vector z, which is drawn from very simple Gaussian noise, as an input, and then we can output very complex images, right? So if we can train such generative models, if we have such generative models, then which assumed to be trained very well and can be represented as a SOM, then we can use this generative model in our MCMC study. Okay, so then of course there are many generative models, but here in this talk I just want to focus on the generative adversarial networks. So briefly, the generator adversarial networks, or GANs, have two networks: the generator network G and discriminator network D. Right. So then, and G and D will be competing in the adversarial process in which the generator want to fool the discriminator D, and the discriminator want to distinguish between the real and fake images generated by the generator. So then what we have is, during the training, the generator will become better and better in terms of, fooling the discriminator, and at the end, it will produce very realistic images, right? So after that, we can just throw away this discriminator and then just focus on the generator, which takes the latent vector Z, sampled from Gaussian noise, and then have our fake images generated. So then here I again just show this binary signal detection example, because if we assume that our generative model can be used as a stochastic object model for our ideal observer calculation using MCMC, then everything will be the same as the original MCMC method, right? So we just replace our generative model with the previous stochastic object model, such as the lumpy object model, right? So, but the thing is that if we use this generative model, it will be very, it will be very easy to calculate these, these probabilities. For example, this P sub Z, which is a prior probability, is just a Gaussian, okay? That is defined in the training. And here just summarizes the framework of this MCMC-based ideal observer computation using GANs. First, we train, if we have data, then we can train a GAN or other deep generative models. But here we just focus on GAN, and then we take the generator from this GAN training, and then we can just run the MCMC sampler by sampling from the latent vector space. Okay. And then after we have done this, we can collect these EKE likelihood ratios, and then subsequently used in the Monte Carlo integration to compute the final ideal observer test statistic, and then finally produce the RLC curve. Okay, so it will be, I have talked about, so many, ideal observer stuff without any constraints, right? So which means that, okay, we can use those upper bound as a figure of merit to assess the total amount of information in images, which is nice if we can maximize that. And of course, and as I also mentioned that, besides the image quality, the perception process will also affect the diagnostic performance, right? So it will be important to also investigate, to explore what will be the optimal way to interact with images when we are considering about some constraints on human visual system. All right. So then here I show a visual search study example. And for example, because human eyes have photoreceptors, for example, cones and rods that are non-uniformly distributed in the retina of the eye, then our human will encode a large field of view with varying resolution, right? So then we heavily rely on direct our fovea, which is the most sensitive part or the highest resolution part, to the target of locations. So then good search performance is very important for survival. So it might be true that humans have evolved to have very good search strategy, right? So to figure it out, or to evaluate the efficiency of human visual search, it will be important to have another model, the foveated ideal searcher or the Bayesian ideal searcher. All right. So then in their 2005 Nature paper, Najamny and Geisler proposed the Bayesian ideal searcher model that optimizes the eye movements for Gaussian temporal responses, right? So that one is very complicated to compute even for the Gaussian response. So then that will be intractable to compute if we consider more complicated cases in which the temporal responses are no longer Gaussian, right? So again, when our problem is very hard to solve, or it is difficult to compute directly, what we want is to seek the help from machine learning. All right. So then for such task, because we want to take a sequence of actions, so then reinforcement learning might be a good choice, right? So in reinforcement learning, there are two fundamental elements: the agent and environment. The agent is an algorithm, and the environment will be able to interact with agent, right? So the agent make an action, and then the environment takes the action and then subsequently update its own status, and and provide a reward to the agent, right? In our case, the agent will be the one to select the next fixation. All right. So the environment can be, in our case, is the time responses from the image data at the fixation, right? So then we all, by use of this framework, we explored the Q-learning, which is a type of technique in reinforcement learning, in which we want to optimize our action according to this so-called Q value, which is the expected reward for a given state action pair. Then, if we have such reward for each state, right? So then we can choose the action that maximizes this expected reward. Okay, that will be our optimal fixation location. But actually, it will be not feasible or not scalable if we want to compute, this expected reward in the entire space of this state action pairs. So then, what we want to do is to use neural network to approximate that. Okay, this is a Q network. We also did some network studies. Basically, we first tested it for a Gaussian case in which we can analytically compute the ideal searcher. And then we'll compare our Q network searcher with that ideal searcher and find that they have a very similar performance, which is a proportional correct performance. And then the spatial distribution of fixations were also very similar between the ideal searcher and the QNet searcher. We also tested for the non-Gaussian case, in which we also use the ideal searcher that was developed for Gaussian case and directly apply that to the non-Gaussian case, right, to compare against with our model. So then the ideal searcher with assumption of Gaussian for this non-Gaussian case would be performing worse than our Q network, okay, in that case. So to summarize, Bayesian searcher is a powerful tool for image size and vision size, and then we can use that to optimize imaging system parameters and understand or model human perceptual processes. But there are challenges to compute the ideal observer. And in this talk, I just introduced some of the machine learning methods that will be possibly very useful for performing such tasks. Okay, I'd like to thank Dr. Mark Anastasio, who is currently the head of bioengineering department at UIUC, for being my PhD advisor, and Dr. Miguel Axton, who is a distinguished professor in the department of psychological and brain sciences at UC Santa Barbara, for being my postdoc supervisor, and they all trained me well in this image science and vision science, and really enjoyed such research work. And also finally, there is a brief announcement or advertisement. So we'll be having 3 oral presentations in the upcoming SPIE medical imaging, and these 3 papers correspond to distinct 3 topics that I have not mentioned in this talk. On the left, there is a new method I proposed to establish efficient channels for approximating ideal observers. In the middle is the one that tells us how to incorporate numerical observers in the image processing algorithm, such that we can have a better perception on the signal to be detected. And the third one is the one that incorporates the generative adversarial networks, diffusion models under the framework of ambient GANs to be able to stably train SOMs from noisy image data. So and also I'm established my new lab here, which has named Computational Imaging and the Visual Intelligence Lab, or in short, CIVL. So I'm also actively looking for students or collaborators. So if you are interested, I'm always happy to talk. And that's my talk. Thank you all for attending.
Any questions from the audience?
Awesome. Great talk. Thank you very much.
Yeah,
So I have a question regarding, you showed at the beginning that in the forward problem, you generally in imaging, you get the measured data, and then you can try to reconstruct the image for interpretability, basically, among doctors. So I assume, of course, that this reconstruction step would introduce more noise, right, in the images. So why not try to solve for the vision ideal observer just directly on the measured data? Why are we trying to do this training on the images? Why not just do it on the data at the beginning?
Yeah, that's a great question. So basically, so if you, it is true that, so natural data will have the total amount of information, right? So any, reconstruction algorithm will not be able to add more information to the natural data. So this is why we have also advocated that the ideal observer should be directly employed on measurement data to get the upper bound of the performance, right? So there was a paper from also from Dr. Anastasio at UIUC that showed that when we evaluate the observer's performance for reconstruction algorithms, they used the measured data and they calculate the ideal observer in the measured data space to get that bound. But it is also important to have the reconstruction part because AI has not been able to replace human, right? So radiologists and doctors are heavily involved in interpreting images every day, right? So then what kind of image processing or reconstruction or enhancement or even display can enable the doctors to see tumors better? That is also very important. So this is why it will also be important to investigate ideal observer studies on the image domain, in the image domain. Yeah.
Actually, because it seems like you've defined the pixel domain and the measurement domain. Those are kind of arbitrary definitions, right? That you could think about.
Oh yeah, right.
Different feature representations of the data.
Yeah.
Isn't that like you've defined the problem specifically on some domain, but defining the basis would affect the problem deeply as well.
Right. So what I'm getting is that is the definition between the measurement data or the specify.
Both of the definition of what's a pixel and what's a measurement are kind of arbitrary.
Actually, it's right. Typically, the measurement data refers to the one that the data that collected from the device.
Before you even start the problem, you've already biased the system.
Oh, why is that? Pretty more.
Well, because like you have a system, you're going to extract data. When you decide, okay, that's a measurement, and then when you say, well, that's a pixel, that's all.
One applied for the measurement data, another one for the image reconstruction. But this is kind of the different problems. Yeah, so to me, I think that's just different problems, right? You want to address. One thing is that you want to measure, how your device can collect, data, and in which the information is contained. And then another problem is, if you have some processing algorithms, after that you apply that, then what will be the information on that, right? So there will be separate problems on that to me. But exactly. The answer, exactly. I agree with that. The answer can be different, right? So for example, the one that has the best performance on measurement data doesn't mean that after some sort of the algorithms or operators, it will still have the best performance on the other observers, right? So for example, there are the channelized observers, the anthropomorphic observers, right? So they may not be totally consistent with the ranking of the ideal observer on measurement data. But that depends really on the situations, right?
All possible. The ideal observer would be overall possible ways of representing the data, right?
Exactly. Yeah. Right. So then again, that's two separate problems, right? That's two separate problems. One is that you want to evaluate your measurement data, so how your device will be able to acquire information according to the image device. And then another one is how do you assess your reconstruct images by use of ideal observer. So I think that's two separate questions, and both are valuable to investigate. Yeah.
The actual one way or another, we have a patient with a tumor. So if you now have one observer set up that's based on the created image data, one that's based on the raw measurement, one that's based on something totally different. When you're really talking about absolute performance out in the field where reality may or may not, well, it certainly will not to some extent represent the statistical distribution of the data that you trained on. So you're depending on generalization beyond the original input.
Yeah.
How do you come up and decide which answer is better?
I think that's a great question. And to be honest, I don't have a very direct answer to that, but I think it is an ongoing research topic. For example, how do you evaluate your generative models in terms of the distribution from the generated data versus the real measurement data. So I think that is also being actively explored, and I think that will be a very interesting topic for future investigation.
I found myself thinking in this presentation that throughout a lot of it, very little of it was actually specific to imaging in medical. It was about signals, distributions, and decisions. And I'm wondering what other communities face similar problems that may have nothing to do with imaging, and do they similarly drive advances in the analysis of this field, or is it really all about imaging? And because it seems like most of what you showed isn't necessarily about imaging.
Yeah, exactly. I totally agree with that. So the statistical design theory behind this work is actually also applicable to many research fields, such as people are also using ideal observer for investigating vision, not only the human vision but also the other vision. But of course that can also be extended to other signal processing community, right? So but as far as I know, this set of tools is very useful, particularly in medical imaging, because there is a need to actually evaluate medical imaging systems in terms of a specific clinically relevant task, right? But to be honest,
you could say the stakes are very high. But it also, is that an incoming missile or not? It also has a lot of consequence too. So
it's a detection problem, though, right?
Yeah,
So
exactly.
So the likelihood ratio that they have.
Exactly. Yeah, that's another thing.
But maybe some of the problems would be something like drug resistance. And you want to separate two populations, right? And you don't want to make a mistake.
Very, very similar stuff is used in medical diagnosis from other measures, non-imaging.
Yeah, so I'm also very excited and happy if anyone want to collaborate with me for this ideal observer things, and see if this set of tools can be used in other fields. That would be very exciting to me as well. Yeah.
And maybe one last notice is that usually for radiologists, when they try to diagnose based on just the results of imaging studies, they also have some sort of information that are not captured by images, like the clinical history, all of these more or less, they bias the differential diagnosis that the radiologist has just from looking at the images.
Exactly.
So I'm not sure if these bios or these models that are trained through neural networks, they would be powerful enough to even capture these missing information.
Yeah, that's very interesting because incorporating non-model data will be a very a rich field on this topic, right? So it'll be very interesting to investigate if the other kind of data associated. Yeah, exactly. Yeah, that would be very interesting. Great comments.
Population. You don't realize it's a different population because it's based on a parameter that you don't know the significance of yet.
Yeah.
And you come out with completely wrong diagnosis.
Yeah, that's interesting.
Never diagnose just from a single study. You have to.
Exactly. Yeah.
See, so the generation of data may be deficient in that sense.
Yeah. I think that would be interesting.
Well, that has been very interesting and interesting discussion. If you have any questions, come to the podium. Thank you for coming.
Thank you.